Hello, everybody, and welcome to another wonderful day of chemistry. So last time we went through and talked about all the various types of intermolecular forces, from weakest to strongest. Now, what we need to do is ask, well, why on earth does that matter? And so I want to take a quick moment to talk about some of the big applications of IMFs. So there's two major things we're going to be looking at. The first of which is that IMFs tend to tell us a lot about phase formation. They tell us which molecules are likely to form solids, which will form liquids, and who just doesn't have enough IMFs that they can't form anything at all. And this will be the focus of the next several lectures. However, I want to take a quick moment to talk about another really important implications of intermolecular forces, and that's simply how likely are two systems to mix. So if I've got two different molecules, different IMFs, same IMFs, how are they going to hang out? And in general, the rule is called like attracts like. And this is the idea that similar IMFs tend to attract each other more. And it happens kind of in the same way that you'd expect it to happen in high school. Now, in the high school analogy, ions are the cool kids. They have quite magnetic personalities and everybody wants to hang out with them because they have full charges, and charges is what causes IMFs to work. So it doesn't matter who you are, you want to hang out with the cool kids, but the cool kids want to hang out with the cool kids. So ions tend to prefer to hang out with ions, and this is going to generate a lot of ionic solids. Now, next category is polar molecules. They have partial positive and partial negative charges, so they can actually hang out with ions. They like to hang out with ions. They have enough charge that they can hang out with ions. And so they want to hang out with the ions. However, there's usually only so many cool kids to hang out with. So the polar molecules are more than happy to hang out themselves. So in general, if you mix a polar system like water with an ionic crystal, water is quite polar. It has those hydrogen bonds. So it can actually have enough water that it says, okay, there's enough hangers on that water can hang out with the ions and break them up and spread them out because, well, ions like to hang out with ions. There's a lot of kind of cool kids to hang out with. And so you see a lot of those same dynamics you see in most high schools. And again, the more polar, the more popular you are, the more likely you can hang out with the cool kids. Now, at the bottom of the totem pole in IMFs is nonpolar molecules. Now, nonpolar molecules are kind of the odd kids. They like to hang out with anybody. They want to hang out with everybody. But it turns out that they don't have enough charge that anybody wants to hang out with them. And so it's often said that, fatty molecules, nonpolar molecules come together and they cohese. They come together, they form solids or fats. But in general, what actually happens is that everybody else says, I don't want to hang out with you. You go hang out with each other. And that's why nonpolar systems tend to get left behind. If I try to, say, rinse a grease stain with water, the water says, nah, don't want to. Not going to hang out with them. They aren't cool enough. And so it's not so much that nonpolar molecules attract nonpolar molecules. It's simply that nobody hangs out with them, so they're all left together. They're that odd group of kids in the corner of the cafeteria. Now, what we can do is use these knowledge of IMFs and come up with quite cool solutions. And we've done this for time immemorial, and turns out so has biology. So how soaps and cell walls and many other materials work is what they do is they try and do things like tie an ionic end, so a popular kid, on the end of a fatty chain, where it's just carbon and hydrogen. Nobody wants to hang out with that nonpolar grease. And so how soaps end up working is they form what are called micelles, where you have water will end up wanting to hang out with all of these cool ions on the end. And so we have water hang out with all of these ions, but the water doesn't want to hang out with the fat. So that hydrocarbon end gets shoved into the center, forming, again, this micelle, this bubble. And so all of the nonpolar stuff ends up getting stuck in the middle, and the ions are able to hang out with the water and hang out over here. So you end up with this cool double layer. All the popular kids, the unpopular younger brothers who get tagged along and hang out with each other. And that's generally what ends up happening. And this is how soap can collect things like dirt and other nonpolar molecules, because all that dirt says, hey, I don't want to hang out with anyone. Nobody wants to hang out with me anyways. Can I hang out with you? I'm big enough and I have enough polarizability that I can get involved. And that's really the nature of how cleaning works, is it's a clever way of trying to match up how you can get two materials to mix together so you can clean off a surface. So this will hopefully give you a new perspective of what to do the next time you find a greasy mess on your floor. Till next time, take care.